The second process we're going to look at here is basically the first one, but in reverse. So here we have a vector that is in angular notation, and our goal is to convert it to Cartesian notation. Now, before doing anything, the very first thing you're going to want to do is you're going to want to draw it again on a Cartesian plane. This just makes your life easier because it allows you to add things like sines in at the very end. And if you're using right angle trigonometry, not adding the sines into the end is actually really helpful. So let's start off here. If you take a look at the direction, what you'll notice is it is downwards and to the left. There are four quadrants or four sides of the Cartesian plane, 1, 2, 3, and 4. Since we're going down and to the left, what we know is that our arrow needs to be this way. Now, the other thing that we can look at in terms of the direction is along which axis we start. So you'll notice that the first direction provided to you in the angular notation direction starts off from the downward axis. This tells us where our angle is. If it starts off at the downward axis, our angle, which is 0.57 radians, needs to be here. You know this because this direction is first, and it's the one that the angle has to touch. Now, with that being said, just like before, we're going to want to enclose our vector and create a right angle triangle. This probably goes without saying, but you're going to really want the angle to be in the triangle. Don't make a triangle in which the angle is not inside it. It's counterproductive and doesn't really help. And lastly, we do know what this angle is. It's 0.57, and we know that the hypotenuse or magnitude is 5.2. All right, so with that, we have our picture created. We know here that theta is equal to 0.57. Now, with that being said, when we convert this to Cartesian notation, we want to know two things. First of all, we want to know the vertical part, which I'm going to indicate here with y, and a horizontal part, which I'm going to indicate here with x. If we have x and y, we can put this into Cartesian notation very quickly. Now, I'm going to treat everything as positive here, and then when we do our final step, we'll add in the signs. So to start off, I do need to find these two sides, and I have 4 standard trigonometric tools that I can use here. How you do it is up to you. You can pick whichever one you want. Sometimes they just won't work because you won't have enough information in it. But the easiest ones to pick here are sine and cosine. The reason why they're the easiest ones to pick is because they have two of the things we already have. They have the hypotenuse in them, and they have the angle in them. So that naturally suggests which ones you're going to want to use. Again, they're all interchangeable, but these are the easiest ones because they have the things that we were provided with already in them. Now, you can start filling these in. If you take a look at sine, the sine of 0.57, again, make sure that this is in radians, is equal to the opposite side divided by the hypotenuse. If you take a look at the picture that you've drawn, the side opposite the angle, the one that doesn't touch it, is x. And this is in turn divided by the hypotenuse, which is 5.2. This is a one variable equation. Now, if the sine function intimidates you, what I recommend you do is replace it with a number immediately. You can, on your calculator, take the sine of 0.57, make sure that your calculator is in radians, but if you do so, what you will get is 0.540. The sine of an angle, literally just a number, and this is equal to x divided by 5.2. You can rearrange this and solve very quickly, basically just by doing a little bit of algebra, and you will get x is equal to 2.81. Now, this x here is a positive number, but what you'll notice is for our arrow, x is actually going to the left. What that means is x is going to be negative no matter what we do. So in our final answer here, when we have vector A, let's make sure that I bold it properly this time. Even though we've done our math and gotten a positive number, we're going to add the sign ourselves. So here for our x-coordinate, we're going to have negative 2.81. Adding the signs afterwards is very easy to do, and I recommend that you take that as your step. That way you really don't have to worry about where your angle is defined by. You can just follow along with the picture that you've drawn. Now, with that out of the way, we're going to repeat this whole process, but we're going to repeat it to find y, the other side. So for this one here, we're going to use the cosine. So our angle, of course, stays the same. If you take a look at cosine, it is the adjacent side, or the side that touches our angle, which is y, divided by our hypotenuse, which is 5.2. Just like before, make sure your calculator is in radian mode, because our angle is provided to us in radians, and we know that because there's no degree sign present. You can take the cosine of 0.57, you'll get 0.84, and this is equal to y divided by 5.2. Again, we can rearrange and solve this for y fairly quickly. It'll give us a y of 4.38. Now, just like before, if we take a look at our picture, you'll notice that we're going down in terms of y. What that means is we're going to add in the negative sign that we require ourselves. Again, we're adding these signs after the fact because when you're doing right angle trigonometry, it does not take into account the proper signs. There are alternate forms of trigonometry, such as the unit circle formulation, which do, but right angle triangles are a little bit easier to handle. All that means is we're going to add the sign in ourselves. And so at the end of the day, we've now converted our thing into Cartesian coordinates. Our vector brings us 2.81 units to the left and 4.38 units downwards. And so we've converted from one form into another.